Hello everyone, welcome back to Turning Turing. In this video, we'll discuss insertion sort. Whether you're new to sorting algorithms or just need a quick refresher, this video has you covered. So let's quickly dive in. Imagine you're organizing playing cards. You pick up one card at a time and insert it into its correct position relative to the cards already sorted. That is exactly how insertion sort works. Start with the second element and compare it to the elements before it. Shift your element to the left till it is smaller. Now pick the third element and keep shifting it to the left until you find the correct spot for your current element. Similarly for fourth, fifth and so on. Repeat for all the elements. You will observe that the array on the left of your current position is always sorted and you are just inserting the current element at the right spot in the sorted portion of the array. So let's take an unsorted array, for example 9, 5, 7, 2. We start from index 1 or 5. We compare 9 and 5. So 5 is smaller than 9. So we'll shift 5 by 1 position and this is how the array will look like. Now we'll move on to the next element or the next position, which is index 2. So we come to 7. Now we'll start comparing 7 with the elements on the left, or we'll try to insert 7 into its correct position on the left hand side. Now we'll compare 7 and 9. Obviously 7 is less than 9, so we'll swap 7 and 9. 9 and 7 will be swapped. So 7 will be here and 9 will be here. Now we'll compare 7 and 5. Now 7 is greater than 5. 7 is in its correct position, so the array will remain unchanged. Now we'll move on to the next element, which is 2. Now similarly we'll try to insert 2 in its correct position in the array. So 2 will be compared with 9. Now 2 is less than 9, so these will be swapped. So this will be the array. Now 2 is again smaller than 7, so 2 will be swapped. 2 is again smaller than 5, so 2 will be swapped. And you'll see at the end the complete array is sorted. So our insertion sort has completed because we've inserted all the elements in the correct position and the result is a sorted array. So let's quickly go through the implementation for insertion sort. So we have written a method insertion sort and the input is going to be a vector or an array that needs to be sorted. So we'll pick each element one by one and we'll try to insert it in its correct position in the left sorted portion of the array. And we'll be picking elements starting from the second index all the way to the last index. So we start from I equal to 1. The element at index I becomes the key because we have to place it in its correct position in the left array, and we have stored I in a temporary variable j because we'll be using this j variable to put the index in its correct position. So what we are going to do essentially is, let's say that this is an array and this is my current element and my j is currently here. Now I'll compare this element with the element on its left. So currently this element, if this element is greater than my current element, then this element should be put here and the current element should be here. So I'll reduce the index for current element by 1 and j will now be pointing here. Now again my current element will be compared with the element on its left. So this is the element. Now if again this element is smaller than my current is larger than my current element, so this element should come at this position and the position for my current element should be here. So I'll decrease j by 1 and bring j here. Again my current element will be compared with the element on the left. If again this element is larger, this element will move here, j will come here. Now it'll be again compared with the element on the left. If this element is smaller than my current element, so this implies that this particular index is the correct position for my current element and j is at its correct position. So now I'll simply replace my current element in this particular cell and now my current element will be at its correct position. So this is essentially what this loop is trying to achieve. We are comparing the current element with the element just next to it on the left hand side, and if the element on the left hand side is greater, then we put the left hand side element in index j, and we decrease the index j by 1, because the correct position for current element is the index next to it on the left hand side, and we keep doing it till we have reached the correct position or the correct spot for our current element. And once we have reached that position, j variable will have the correct index stored, and at that correct index we just put the key, and key is representing the current element. So once we repeat this for all the elements starting from the second element to the last element, our entire array will be sorted. So the time complexity for insertion sort is actually interesting. So the best case time complexity for insertion sort is big O of n. That is the case when the array is almost entirely sorted already. So in this particular case, we start from 6. 6 will not be shifted because it's already in its correct position. So there will only be one comparison for 6. Again for 7, there will only be one comparison, and we'll see that it's in correct position. Similarly for 8, similarly for 9. So there will be only one comparison for each element. So the total time complexity will be big O of n. And the worst case and the average case time complexity are big O of n square. So the worst case is when the array is sorted in decreasing order and I want to sort it in ascending order. So in this particular case, 8 will be compared once. There will be 2 comparisons for 7. There will be 3 comparisons for 6. So the total comparisons for a array sorted in descending order will be 1 plus 2 plus 3 plus all the way till the last element, which will have n minus 1 comparisons, and we know that the sum of this series is of the order of n square. So the average and worst case time complexity turns out to be big O of n square. Now some pros and cons of insertion sort. Insertion sort is very intuitive and it is very easy to implement, works well for small or nearly sorted data, and it's a stable algorithm. It's a stable algorithm because we are only shifting the current element if it's smaller than the element on the left. If it's equal or greater, it will stay in its position. So at the end, in the sorted array, all the elements which are equal will retain their original ordering. And also it's an in-place sorting algorithm, because the space complexity for our algorithm is big O of 1. We are not using any additional space. Some cons of insertion sort: it is inefficient for large data sets because the worst case time complexity is quadratic n square, and it becomes lower as the input size increases. So yeah, that's insertion sort for you. Simple, intuitive, and a great learning tool for understanding other sorting algorithms. I hope this video helped. In case if you still have any queries or doubts, do drop them in the comment section below, and I'll see you in the next video. Till then, take care and keep learning.